Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. For this episode, I speak with Simon Shaw and Arvind Sharma on July's The Leading Edge that highlights machine learning applications. Simon and Arvind discuss what problems machine learning successfully solves, the requirements and limitations of machine learning, what the next 5 years hold for the topic, and more. For their full biographies, read the show notes for this episode on your phone or at seg.org/podcast. The show notes will also link to the articles discussed in this episode. Subscribers can read the full articles in the SEG library, and everyone can read the abstracts for free. A brief editor's note. Due to Arvind's recording location, he is hard to understand at times. Please continue to listen as his contributions to this discussion are invaluable. Now, for our conversation. Machine learning was last highlighted over 2 years ago in TLE. What have been some of the major changes in that time that have warranted another look at the topic?
I would say, for one thing, the interest in the topic from the greater SEG community has been one factor that precipitated having another look in TLE. If you look at the number of papers submitted to the SEG on machine learning last year, I think that's a pretty good barometer of how much interest there is and how many exciting applications people are finding for machine learning. I'll say also, I think in the past 2 years, 2 years ago, the section was titled Data Analytics and Machine Learning, and I found that a lot of my peers struggled a bit to define data analytics and how to differentiate it from a lot of what we do conventionally in data processing and analysis. What we wanted to do this time was specifically focus on machine learning and deep learning and its application.
I'll add a little bit to Simon's point that a couple of years back, we were still investigating whether machine learning will be helpful in geoscience as a whole. And now I think that bridge is crossed, and we know that it will be helpful. Now we are looking into where all it will be helpful and how much it will be impacting our discipline.
You all stress in the intro, and one of the papers attests to this, that machine learning is not particularly suited to solve all the problems of the world. But however, when is machine learning particularly successful in geophysics?
Machine learning is really good at solving problems which are not compact form. When I say which is not compact form, where physics is very complex and we don't have a direct way to solve this. For example, picking a horizon or filling data, and basically any problem which requires thousands of variables to interact with each other. I think those are the problems that machine learning is very good at solving, and we are seeing those impacts in geophysics, especially in the interpretation field and the data filling problem, denoise kind of problem.
The success is often proportional to the amount of representative training data that we can either create or acquire. That representative data generally needs to be large and diverse. It's got to, as I said, represent the problem adequately. So good training data, I think, is the key to success. And then specifically for supervised learning, that data always to be reliably labeled. So that's another, I think, key to success.
Lee et al. Joined both conventional methods with machine learning using 3 examples, including 2 field examples. What did you learn reading about this hybrid model of theirs?
I think the paper illustrates nicely how machine learning can augment existing conventional methods. In other words, not necessarily replace a conventional method that is usually based on a physical model. That was one key learning from that paper. And then method is also an example of how machine learning might prove efficacy of an existing approach, that is the conventional physics-based approach, and not necessarily just improve efficiency. In other words, machine learning could also make results better, not necessarily always deliver them faster.
Peters et al. Helps highlight the topic of network-based learning methods through looking at its similarities and differences with forward modeling and inversion. What might a geophysicist trained in forward modeling and inversion recognize as opportunities for machine learning to help address?
At the core of it, as we discussed earlier, especially deep learning methods, the network-based learning method, has the similar structure as on the conventional inverse problem that we solve. So what it does, it helps us reorient how to actually frame a problem that we are used to thinking as an inverse problem into a neural network problem, since the underlying principles are very similar. So I will say that it helps us to restructure our FWI and RTM and other problems, how if you want to map it as a deep learning problem. It gives an avenue to think like.
SEG, along with AAPG and SPE, just last week were hosted a couple weeks ago, hosted the Energy and Data Conference. And we expect another strong presence at San Antonio at SEG's annual meeting on machine learning. When SEG returns to Houston in 2024, 5 years from now, what do you think the machine learning session at SEG will look like?
I will say that there won't be, like right now, we are seeing a lot of separate machine learning sessions. I think by 2024, 2025, it will stabilize to the plateau of productivity, in which there will be only few isolated machine learning sessions. And those will be dedicated to more like deep challenges in machine learning and how to apply which machine learning is more applicable for geoscience. Most of the current machine learning users will go back into regular geophysics. So there won't be a separate machine learning session for how to use machine learning in RTM or FWI or interpretation or denoise or so on and so forth. They all get actually pushed to their own session. So basically it becomes a base. Just like we don't talk about computer, we don't talk about programming language, we don't, because they are required to solve a geophysics problem. This will become a fundamental, machine learning will become almost fundamental integrated effort to solve the geophysics problem. So it will move from a separate big session to like it will get integrated in every session.
Sorry, I agree with Arvind. Perhaps machine learning won't have its own session at all. It's unusual for a solution or a method to have its own session or sessions as machine learning does today. And it'll most likely infuse many other sessions.
What problem are you both most interested in machine learning solving?
That's a good question. I think perhaps interdisciplinary problems. I think, for example, today a geophysicist may hand off data to a geologist and then, or else to a reservoir engineer. And oftentimes these are the same data. A specialist may just look at it in a different way. But a machine learning algorithm is of course all about the data. It's in principle not coming at the problem with any necessarily any particular point of view. So I think I'm most interested in seeing how we can bridge multiple disciplines and solve overarching problems with machine learning.
I mean, so I totally agree with Simon on that. And I'll just look this problem from slightly different angle. That means I want to solve most of those problems which are very subjective. If I already have a very good way to solve those problems, I'm less interested in that problem. I'm interested in problems where because of its interdisciplinary nature, because of its complexity, it's very difficult to solve. And if you give the same problem to five different people, you'll get five different answers. So can we actually use machine learning to get something consistent for that particular set of problems?
What do you both hope readers of these 5 papers in this special section take away?
I expect, like as an editorial group, I think we expect the readers of these 5 papers should take away that machine learning has actually got a little bit more maturity in our discipline as a geoscience, and it's able to solve or give solutions to several style of problems. It's not just a niche problem, but now it's proliferating into different solution space, all the way from academia to people who are doing production work. They are using machine learning to solve problems. From Lee et al., who is using hybrid approach, to Peter, who is actually giving the theoretical framework, to others who are actually using only machine learning to solve. So the full spectrum.
Yeah, thanks, Arvind. I hope the readers of these papers come away informed and encouraged. There's a paper that can be as a tutorial that perhaps demystifies neural networks to those that haven't studied them before, and relating it to the classical deconvolution problem for reflectivity from a seismic trace. And there's a paper also that we've talked about that relates deep learning to traditional geophysical inversion problems and the forward problem, how they relate. And then and that they can be encouraged by the examples that are shown where machine learning is deriving significant value for real problems, such as in noise attenuation and fracture event detection, horizon and fault picking, automated fault picking and automated horizon picking.
Is there anything I should have asked about this special section or topic that I did not?
I think I'm not saying this should have been a question, but one of the existing challenges is still with respect to data through flow, I think, and data standards and data labeling, data formats. And as we mentioned in our introduction, SEG members should be aware there's a new SEG SEAM project that's in the works. There's also some other industry initiatives out there that are aimed at trying to crack that nut. I think we can accelerate the applications of machine learning if, as a community, we agree on certain standards for data formats and data labeling.
I agree with Simon that if you ask, the biggest challenge that we face in machine learning is getting the data organized, level, curated to feed into machine learning solutions, because most of the true development of machine learning is happening already with or without us. We are mostly a consumer of the machine learning algorithms. However, we have to actually think through the problem, all the data needed, all the different type of data needed to solve that problem, and accumulate, aggregate that. And that becomes the hardest problem. So that's one more thing that place where I think Simon and I will disagree is the use of real data versus synthetic data. I think Simon will be on the, not trying to put words in your mouth, Simon, but Simon will be a lot more for synthetic data, and I am a lot less synthetic data, because from my point of view, I'm looking at machine learning as solution for complex problems where physics is complex. Hence, we don't have a compact form equation to solve that. If we don't have a compact form equation to solve that, and the physics is so complex that we can't derive a partial differential equation to describe that, then any synthetic data that we use for solving that will basically limit our solution space. And whereas at best it can be a regularizer, and worst it can be actually wrong and it pushes in the linear direction. Whereas if we truly want to capitalize on machine learning, then we need to reduce the synthetic data and go more and more for real data. It's a harder problem to leveling real data is way harder than leveling synthetic data, but that's what we need to do to truly capitalize or get the most benefit out of machine learning.
Actually, I totally agree with that point. I think the use of synthetic data is, I would say, limited to cases where the problem is not complex and where we can model it significantly. Objective for using or for considering machine learning in those cases is less to solve a complex problem and more to solve a rather simple problem, but much faster. I think, for example, the automatic fault picking or automatic horizon picking, we can generate quasi-realistic synthetics and have already shown pretty good results. We're automating a process that's relatively simple, and that's the value there. But you're right, we can't model complexity that we don't yet understand.
Well, gentlemen, I appreciate you joining with me today to talk about this special section and for volunteering your time on helping edit it and organize it, and look forward to hearing the feedback from the papers.
Thank you, Andrew.
Our pleasure. Thank you.
Please share this episode with a friend, colleague, or manager that would enjoy hearing this episode. Your recommendation is the single best action you can take on behalf of SEG's podcast. Go to our website at seg.org/podcast to find all our episodes and learn how you can subscribe for free directly on your phone. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. The SEG podcast team is Jennifer Crockett, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.